Yeah, thank you so much. And I also would like to thank the organizers for inviting me to this excellent initiative, the really successful one. So I'm going to talk today about our numerical modeling results on the formation and evolution of transformed continental margins. And particularly, I address the question, what are the links between active tectonics and their surface expressions during the different stages of transform margin formation. This talk is based on a recent paper of ours that can be downloaded from the Geological Society London website. This model study is not site-specific in an attempt to remain generic and address the main driving forces and physical controls for transform margin formation. But of course, the model parameters have been inspired by observations from well-studied areas such as the equatorial transform margins or the evolution of Madagascar, West Africa. So the formation and evolution of passive and transform continental margins are genetically connected and represent vital processes in plate tectonics during continental rifting and the opening of oceanic basins. Transform margins are indicated by thick black lines on this map, and they are either perpendicular to passive margins or they show an oblique angle with respect to the bounding passive margin segments. On this very simplified Mickey Mouse sketch, I tried to illustrate the main features and geometrical relations between the oceanic basins, the continents, and the intersections between transform faults and the continents. And this can be classified into the outer and inner corners that are characterized by distinct features that can be addressed by the means of numerical forward modeling. And classical models assumed a rigid kinematic evolutionary model where extension perpendicular strike slip faults have been reactivated or activated from the onset of rifting, ultimately connecting active mid-ocean ridges. And we will also revisit this idea by the means of modeling. So transform margin formation during the overall oblique and diagonal opening of the Atlantic, for instance, is associated with a few common features observed at many locations, as we also saw it by this very nice and inspiring compilation by Lieslonka and co-authors. So among others, one can observe anomalous elevations in oceanic or deep marine domains. Here you see a comparison of a classical shoreline shelf break and slope diagram from a continental margin. Very similar locations, one can observe these nice marginal plateaus, as we have seen. And in other locations, narrower transform ridges are observed, like in the case of this example from the Côte d'Ivoire margin. And the line drawing interpretation of this reflection seismic data also shows this nice transpressional structure that indicates transpression or inversion and related uplift. So the location of transform faults and transform margins not always, but often coincides with inherited structures from preceding tectonic phases and related structures. In the case of the Central Atlantic, early Cretaceous rift initiation was dominantly controlled by inherited Pan-African shear zones. Furthermore, tectonic reconstructions often infer unichelon geometries of rift structures, where the rift zones and later the oceanic basins are propagating towards each other, creating transfer zones, like in the case of the reconstruction of the Davis fracture zone. So these inferences inspired many modeling studies that address the evolution of transfer zones resulting from two evolving rift zones initially localized by thermal or compositional heterogeneities. Other studies also address the role of more complex weak zone geometries. So in this study, I will focus on the links between surface processes and rifting during the formation and evolution of passive and transform continental margins, and that particularly address the role of erosion and sedimentation and the influence of different crustal or lithospheric mantle inherited weak zones. So as for the methods, I used the 3D thermomechanical code I3Elvis that is being developed at ETH by Taras Geria and his group. We solved the conservation equations by an finite differences and markers in cell technique. And in this study, I simulated lithospheric extension resolved by 1 kilometer uniform grid spacing. My models included simplified parametrization of partial mantle melting, magmatic accretion of new oceanic crust, and hydrothermal circulation along the mid-ocean ridge axis, leading to excess cooling. Furthermore, surface processes such as erosion and sedimentation has been implemented by a diffusion-based approach of FDSPM, that refers to or simplified diffusion-based finite differences surface processes model. So there's a full coupling, a two-way coupling between the thermomechanical code and the surface evolution, including erosion and sedimentation. So we built a model domain consisting of upper, middle, and lower crustal, lithospheric mantle, and astenospheric mantle layers. Rifting and extension is simulated by divergence boundary conditions on the left and right model sides. Free surface is imitated by a low density, low viscosity air layer on top, and therefore we can simulate the topographic response. The model used temperature and pressure dependent thermal conductivities and densities. We assumed viscous and plastic rheologies. Strain is initially localized along two weak zones placed in the upper crust in an unichelon geometry representing inherited thrusts. And then in a series of models, we tested different initial weak zone locations, different extension velocities, different rheologies, different imposed diffusion coefficients that meant different erosion and sedimentation rates. So here you see the evolution of the reference model by the means of rock composition at two snapshots, and you see the evolution of the strain rate. So basically what is yellowish, you have ongoing deformation initially along these two weak zones, and finally we reach crustal breakup, oceanic crust formation, and you also see how deformation, the side of deformation changes within the transfer zone, and we also extracted the surface heat flux evolution. As for the phase composition, so during lithospheric mantle thinning, at a certain stage, we reach mantle melting. You see the area of partial melting by this red color, and the melts are extracted to shallow magma chamber that will lead to the formation of oceanic crust that is indicated by green. And the sediments that are deposited are indicated in yellow color and are visualized in a semi-transparent way, and therefore we can see what is underneath. So here I just show you two cross sections, one extension parallel and one orthogonal, showing the evolving passive margin and transform margin. So deformation is initially localized along this weak zone that gradually evolves into a metamorphic core complex, while deformation eventually migrates laterally until we reach crustal breakup and oceanic crust formation. I will go through the distinct stages of the evolution along the passive margins, and I will also focus on the evolution within the transfer zone. So here you see three characteristic snapshots of the phase composition and a few steps showing the active deformation, and here I extracted the subsidence and uplift rates. So initially, deformation migrates laterally from this weak zone towards the final localized rift arms that are propagating towards each other initially within the transfer zone. Basically, tip splay faults and gradually rotating oblique normal faults are observed. During a more major stage of rift linkage, proto-transform faults connect the major rift and the mid-ocean ridges. During the propagating evolution, basically the strike of this connecting proto-transform gradually rotates into a more and more orthogonal position. Within the continental sides, some of the abandoned pull-apart basins and proto-transform faults can be observed, bounded by ridge geometries, while newer proto-transform faults connect the propagating mid-ocean ridges. A very important stage is this last moment prior to breakup within the transfer zone that basically coincides with a large continental oblique extensional pull-apart basin formation. You can also see that deformation is much more distributed within this transfer zone. This also leads to mantle exhumation within this large pull-apart basin, and during this shearing, in fact, significant marginal uplift occurs besides the ridge and pull apart evolution. And finally, breakup also occurs here. There's a zone of mantle exhumation within the transfer zone, but finally, two stable transform faults separate the transfer zone, and also a new mid-ocean ridge and transform spreading occurs in the center. So if I have a closer look to this stage of 8.3 million years, here I just show you a same zoomed image of this stage and a few cross sections. So let's take a look, for instance, of section C and D that are located at these two extension orthogonal locations at the center of the model, and here this A and this cross section that indicates the intersection of the ocean and the continent. So within this region, basically the abundant pull apart basins and some marginal ridge can be observed, whereas in the centermost part during this last stage of rifting prior to breakup, distributed deformation leads to mantle exhumation, and this also coincides with this lithospheric scale updoming or uplift that leads to these marginal elevated locations. You see here the topographic evolution of this stage, and due to the uplift of these arms, basically sedimentation reorganizes because it cannot go towards these elevated areas, and sedimentation and sedimentary pathways ultimately concentrate towards the inner corners, while the outer corner remains sediment starved. And later on, during the post-rift stage, these previously elevated locations also submerge beneath sea level, but still they represent an elevated bathymetric area. This can be called as marginal plateaus. And these observations, as for the sediment pathway reorganizations, are in good agreement with observations from seismic and well data, as shown here by the compilation of Gábor Tari, who analyzed well data from different transform inner corners and basically arrived to the same conclusion as we indicate by these model results.
You're at roughly 12 minutes. Okay.
Yeah, perfect.
Yeah.
So another observation that our reference model shows is the evolution of continental crustal slivers within the mature stable oceanic transform faults. So basically, this is in also good agreement with observations such as from the equatorial Atlantic, but also from other locations where continental slivers has been reported from oceanic transform faults. And basically these are separated, and these are entrapped within this initially wider transfer zone driven by the inheritance from the rifting stage, and these are entrapped also during the oceanic transform stage. As for the role of surface processes, so it has been shown by many previous studies that sediment loading and enhanced surface processes increase the lifespan of individual faults, but at the same time sediment blanketing increases moho temperature that leads to basically ductile weakening. So first we just run a simplified model without any erosion and sedimentation and with very high diffusion coefficient, and we arrive to the same conclusion of enhanced strain localization in case we have higher erosion and sedimentation rates. So what does this mean for the case of transform formation? Here you see a comparison of two models with two different diffusion coefficients, but otherwise all the other parameters are identical. And what you see here, that in case we applied higher erosion and sedimentation rates, that led to a more efficient strain localization, that also led to an earlier mantle melting due to enhanced lithospheric mantle thinning. And this earlier mantle melting ultimately led to earlier crustal breakup, and that created higher transform offsets because the two rifts localized at a larger distance from each other. As a comparison for the structures, our models show that the models with higher erosion and sedimentation rates leads to narrower passive margins and more focused deformation also within the transform margin side. As for the comparison of crustal weak zone versus a model where we placed the weakness within the lithospheric mantle, one can conclude that a mantle weak zone enhances mantle thinning, leads to earlier mantle melting, and also leads to underplating instead of mantle exhumation and larger transform offsets. So just to wrap up, these simplified model results concluded that transform margin formation undergoes a multi-stage evolution. Lithospheric scale plateau uplift occurs during the last stage of rifting prior to breakup, and sedimentation is focused towards the divergent margin segments towards the inner corners. And with this, I thank you for your attention.
Thank you very much, Balázs, for a fascinating talk. I love seeing the numerical models that include the sedimentation. There is a question already in the chat from Fola. Fola, do you want to unmute and ask your question?
Sure. Thank you, Attila, for your presentation. I was wondering if you observed any increase in strain rate on the proto-transform fault as soon as they linked up the two interactive segments, prior to breakup. Do you see any increase in strain rate?
I see. So because of our boundary condition, in this simulation that I showed you, we imposed basically constant boundary condition velocities. So that is one limitation. But otherwise, what you see is the gradually narrowing zone of the transfer where deformation occurs, right? So basically, if I just go back to this stage, here you see the strain rate evolution that is initially distributed. That's why we rather have mantle exhumation at this stage, because here the crust is thinned while we still have the remaining lithospheric mantle, while in the case of the passive margins, we rather have underplating. But ultimately, this wide transfer zone that initially had distributed deformation gradually evolves into a narrow, transform fault zone that will be, in some cases, overprinted by a transform spreading ridge.
Thank you.
Are there any other questions? I don't see any in the chat, or nobody's got their hands up. Oh, there's a question from Lise. Lise, would you like to unmute and ask your question?
Yes. Thank you a lot for this presentation. It was very interesting. I was wondering if there were specific conditions for allowing mantle exhumation during the transform continental stage, as you mentioned.
Yeah, so basically, we ran many simulations with different mantle thermal gradients, with different divergent velocities, because basically it's a competition between strain localization and mantle melting. So in case we have lower divergence velocities, or in case we have lower thermal gradients, or in case we have rather crustal weak zones, and in case we have a lower sedimentation rate, these all prefer mantle exhumation. While in all the other scenarios, in case we somehow arrive to a more localized deformation and to higher thermal gradient in the mantle, that rather prefers underplating.
And is this exhumed domain large?
So it really depends on the combination of all these parameters. But if I just come back to this region, so this can be in the order of a few dozens of kilometers in our simulation with the higher thermal gradient, and it can be as wide as 50 kilometers in our simulations.